this lecture is, I would say, more in the category of enrichment. So we're talking about chemical evidence, and this is applying the forensic analysis more towards security operations, which, if you think about it, forensics labs and so on, it's it's almost always after the crime. But that doesn't help you in like a mass casualty event, right? You want to stop those before it happens. So you don't want to try to, have thousands and thousands of people dead and then say what happened. I mean, that's a bad situation. Let's try to detect and disrupt before the thing happens. And so that's the security operations thing. The goal is to reduce the threats, and they've sort of got this typical 3 Ds for reducing threats. There's detecting the threats, the threatening events, and supporting infrastructure. There's disrupting those threatening events, and then destroying those threatening events or the infrastructure or the supporting environments. So those are the 3 Ds. And the secondary goal is minimal impact on normal life. So notice that the impact on normal life is secondary, okay? Because again, if we don't impact normal life at all, then that might hamper our ability to disrupt the threats. This is why in some situations you got to go through a metal detector, or you want to get on a plane, you got to take your luggage and take out all the liquids and all of these different kinds of things. Those are disrupting normal life, but it's hopefully balanced by the risk of the consequences. So this is a difficult situation when you have a low probability event with an extremely high consequence. Those are the hardest ones, and those are the ones that that really take some head scratching. Like in your personal life, right? There's it's not probable, say, that you might hit air turbulence that's strong enough to smash your head against the top of the cabin and kill you. And that's a low probability event, but the consequence is really high. And so you put your seatbelt on, right? In the plane when you're, or the door blowing out. Again, not a probable event, but a high consequence. If you're by the door and you don't have your seatbelt on, you're flying for a while. And so those are the difficult things when you have a high consequence and low probability, because you got to do something, but you can't like put yourself in a bubble for a low probability event. So anyway, those are the difficult things. And that's what we have with, terrorist threats and so on with mass casualties. So this threat, we talked before, the previous slide about detecting threats and destroying the capabilities for threats and so on. And so it's helpful to think about threats. Now we're talking about security operations, but you also have this in your daily life too. You have situations that you think, well, this person's upset at me. Do they really have an intent to do me harm? Okay, maybe they do. Do they have the capability to do me harm? Okay, we deal with this when we're dealing with 2-year-olds. They have an incredible attempt to kill you because they're mad. You took away their toy because it's supper time, But do they have the capability? No. So, it's not really a threat. Okay, it's an intent, but not a capability. So we need to analyze these things logically. So the intent to cause you harm, your neighbors, business, and so on, is there in many situations. Personal enemies, ex-friends, competitors, disgruntled ex-employees, other governments. So I kind of failed this question when I had my psych evaluation when I worked for the government. So the psychologist is asking me all these questions. Well, first you take the test. You take this Minnesota Multiphasic Personality Inventory, MMPI, I think is what it's called. It's like 300 questions, and you're going through, and all the questions are kind of gray area, not all of them, but it's like, I'm absolutely not afraid of fire is one of the questions I remember. And I'm thinking, I'm not really afraid of fire, but I can't say I'm absolutely not afraid of fire. I mean, right? And so, strongly agree, what are you going to put on that, right? So, I was like, well, somewhat agree, I'm not afraid of fire. And so you can work yourself, into a frenzy trying to figure out what the right answer to these things are. And one of them was someone wants to kill me. And I was like, man. And this was right after 9/11. And so I'm thinking, well, of course, so Osama bin Laden wants to kill me. Like he's trying his best to try to kill me with planes and all of that stuff. And everybody was just freaked out about terrorism. So I put strongly agree. Okay. It's what, answer first, they say first impression, give your answer, go through. And so luckily, after the test is over, then they have a psychologist. They look at it and they say, okay, we need to talk to him about these three things. And it's classic. You go in, you small talk for a little bit, dips his toes into this area, and you talk a little more. And then he says, so who's trying to kill you? And I said, Osama bin Laden. And he goes, really? I said, yeah. And he said, that's why you answered that question that way? I said, yeah, that's the person. And he's like, oh, okay, no problem. So he writes down. Yeah. He's like, no, man in the closet? No, nobody's in the closet. Yeah. Is he in the room now? No, he's not in the room now. So, and so then the capability. So there's the intent and the capability. So there's a lot of capabilities to harm a single person, obviously, right? But there's fewer capabilities to exact enormous harm. And so what makes an attractive target? Obviously, if you have an intent to cause substantial harm, you want a large number of victims. You want the area confined, a controlled and predictable environment, and a symbolic target, if you can, and a large potential of media exposure. Okay, and soft security, relaxed security. So sporting events, business buildings, air travel, and mass transit, these are fairly soft targets. Going and attacking some military base, probably not a smart idea. But going and trying to attack a baseball game or something like that, again, especially now that we're so far away from 9/11 and everybody's memory of that security has relaxed quite a bit. So, for years after 9/11, we were really worried. Every time there was a New Year's Day event at Times Square, we were just like, man, it's going to happen. Somebody's going to get in there and blow up a bomb or whatever. And they were amazing at how they set up the security for that event. And actually, I think made it better. It used to be, before 9/11, just a massive mob of people, elbow to elbow, drunk. It was crazy and not very enjoyable. It was enjoyable, I guess, for the people that were drunk, but if you weren't as drunk as them, it was probably less of what. So they sold tickets after 9/11, and they had these little, I'm going to call them cages, but they're like little boxes, and you could buy your ticket, and you had your box with you and your friends, and you had a lot of space, and so it was actually more secure and more enjoyable, because it wasn't just chaotic. So that's what they did to sort of make the Times Square New Year's Eve celebration a less of a soft target. And it worked out well. And it didn't just disrupt normal life. Normal life was awful. It actually made it better in that situation. Maybe that's not always the case, but they did a great job with Times Square. And so let's talk about the different agents that might be useful in some of these attacks, and evaluate them against each other, and then ways for us to detect on the front end, before this event happens, of how to disrupt it. So chemical warfare agents are some of the scariest things that I can think of. These organophosphate nerve agents will get in and affect your central nervous system. And one of the ones is these that interfere with acetylcholine esterase. So acetylcholine is a neurotransmitter. It's important in your central nervous system control of your muscular system. So you get a transmission from your central nervous system that allows your muscles to contract, and then there's an enzyme that breaks up that neurotransmitter, cholinesterase. And so if it doesn't turn that signal off, then your muscles can't relax. Okay. So if you were to interfere with the off signal, then the person can't uncontract, okay, which means they also can't breathe, which means their heart can't relax. And so eventually it kills you by you just seizing up and all your muscles tighten up and you can't ever relax them. So that's what's happening with these nerve agents. And the small dose is the toxic dose is really small. So they're very, very bad. Other vesicants, these are, I don't know which is worse. These are blister or mustard agents. They cause your skin to just blister up, and it's awful. A lot of times these, with really good health care, won't cause death. They'll cause enormous pain. Your skin you pretty much have to regenerate all your skin. But what happens is typically people get secondary infections because their skin is so compromised that then they get an infection and die from the infection. Okay. But the thing is, these are incredibly volatile. So vapor detectors can detect them really well. So that's a good thing that we can detect them. So we can have sniffers in the subway, sniffers in the airports, and so on. And if somebody's carrying a substantial amount of this in a bag or a box or a luggage or whatever, it's going to smell. Like to a detector, it's going to stink. They walk by a detector, ring the bell, something's going on. And so this, even though these are terrifying substances, they really are smelly. And so our detectors are able to detect them quite well. Then there's toxic industrial chemicals. They're much easier to obtain. You can find enormous tanks of ammonia like this in rural agricultural areas. You can, bust off the lock and steal quite a bit of ammonia. They use that or steal it for the clandestine meth labs. We've talked about that. Swimming pool facilities have huge tanks of chlorine. And not all facilities use the chlorine tablet. Some have tanks of chlorine, which would be enough to, certainly enough to kill everybody in this room. Okay. Would it do enough for the whole building? I'm not sure. The dose, again, what's our phrase? The toxin is the dose, right? And so these are toxic chemicals at a high enough dose, but they're much higher dose than, say, the nerve agents. And so you'd have to fill a substantial amount of a building with chlorine gas before it killed people. It would kill some people who were closest to the inlet, but in order to create a mass casualty event, you would need train car loads. So now maybe that would be the thing. You blow up a train and it crashes and it releases all of its toxic materials. It's going to flow downhill. It's more dense. So these are all plans of nefarious people. But these are pretty conspicuous. I mean, you're not going to be rolling a tank of chlorine onto an airplane. Yeah. And so you need a large dose of the toxic industrial chemical to create a mass casualty. And they're also volatile. The volatile ones are going to be detectable. If it's not volatile, you need to disperse it. So let's say, cyanide's pretty darn toxic, right? But it's a powder. How are you going to disperse it? Well, you're going to need some way to get it volatilized. And you can't use heat because that would destroy the compound. So you're going to have to puff it somehow. Well, things that explode or puff are also going to be volatile. So you're going to be, the criminal is trying to fight volatility, and you as an analytical chemist is going to use volatility to detect these things. Okay. So here's an example of when it wasn't detected. This was a high explosive attack. Now I realize it was a long time ago, but I still like to highlight this because it shows you the level of investigation that we're capable of. So this plane crashed over Lockerbie, Scotland, killed 243 passengers and 16 crew members, okay, and 11 people on the ground. I mean, they didn't even accept the risk of getting on a plane. They're just on the ground and a plane falls out of the sky and kills them, okay. It was 450 grams of plastic explosives, so 1 pound. I mean, that's a small amount, okay. It only blew a 20-inch hole in the fuselage. So more than 10,000 pieces of debris were retrieved, tagged, and tracked. So can you imagine being on that scene? You've got plane bits everywhere, luggage bits. If it hits a house, how do you know what's plane and what's in the closet? Right? Was this the luggage from the family here, or was this luggage on the plane? And so they collected all of that and put it in. Typically, they pick an airplane hangar and they try to reconstruct the location of the evidence in the hangar so they can see and try to recreate what happened to the plane. Really difficult thing to do because what was caused by the bomb and what was caused by the plane hitting the ground. The plane's all ripped to shreds. So they put it all together. They found a part of the fuselage that had evidence that an explosion had blown a 20-inch hole in the fuselage. I mean, it's amazing. It's hard for me to believe that a 20-inch hole could bring down a whole plane when we just had a plane go without a door, blew out, and it didn't bring the plane down. So it's hard to say when and where the hole is. I'm trying not to scare you to death over a plane, losing it. I mean, I was surprised they were able to land that plane just fine when a 20-inch hole brought this plane completely down. So location of the hole is important. They examined the baggage, and they found high energy damage of some of the bags. Test explosions confirmed the location and quantity of explosive used, and they found a Samsonite suitcase. So they found the actual suitcase that had the bomb in it. It had parts of a circuit board in it and parts of a Toshiba cassette player. We didn't have our phones or iPads, iPods in 1988. If you want to listen to portable music, you had a cassette tape player. You Google cassette tape, you'll see what I'm talking about. Okay, and it's a little thing. Sony Walkman, you've heard of that. That's sort of the brand, the classic. This was Toshiba's competitor, and it was about that big. And so they took all the guts of the cassette player out and put in Semtex explosive. Now this is interesting too. So it's international cooperation. They found this that it matched, the circuit board matched, and the cassette player's way of making a bomb matched this terror group from 2 months earlier. This was seized by West German police. And the circuit board fragment found embedded in a piece of charred material was identified as an electronic timer. So they even found the circuit board that was the timer, and that was tied to Libyan intelligence that had been arrested 10 months previously, carrying similar bomb material. So they even found that the timer was traced to this Swiss manufacturer that went through the Libyan military. So it's pretty impressive investigation. They even also discovered how this luggage made it through the system. So it was checked through, so no passengers. So this wasn't even a suicide attack. They just checked the luggage through to a final destination. So this bag was just being transferred to the plane. And when it was on the plane over Lockerbie, Scotland, it blew up. Okay. So they've changed a lot of the procedures. Like when you're checking a bag through, I mean, they do extra scrutiny and so on. But most of the time you have to go with your bags, and that's where the whole question that you have in the airport, what do they ask you? No, they don't ask that. They ask, has anyone asked you to take a bag for them? Have you heard that question? They ask at every airport, they say, if anyone has asked you to check up or take a bag with you, you don't do that, And they'll ask you at the desk sometimes, or when you're coming through getting your ticket, if there's a change in your ticket, or if you notice a lot of times in making your reservations online, in the fine print it says don't accept any bags for anybody and so on. That's resulting from this.
When you become a flight attendant,
yes.
They teach you how to protect bombs on the plane.
Really?
What positions to locate plane detected with this machine that they look at.
Oh wow.
And then subsequently you learn about what parts of the airplane can fly with holes.
Yeah.
And where to sit to in case you crash where you're most likely to fly.
Wow. Write that up and share it with the rest of us. So I'm going to sit right there. It's the strongest part right there, the center of mass of the plane. Yeah. Snap off, and then that's. Yeah, yeah. That's interesting. Over there, yeah.
There's a bomb on the plane, then you send it to the very back, and it'll blow off the tail, and you can fly the plane to the back.
Wow. That's amazing. Yeah. I don't know if y'all heard that on YouTube, but that was cool. Yeah, but that's also why, that door blew out. That was an overwing exit, I think. Yeah, so right there, the strongest part of the plane. It wasn't whipping the front of the plane or the back of the plane.
A bird or something smashes into like the front of the plane,
mm-hmm.
or like a side piece of the
Yeah. Yeah, that's amazing. I don't like to think about that. Low probability, right? Definitely high consequence, but we hope it's low probability. But because we fly so many planes, there's thousands upon thousands of flights. Yeah. So,
When I was a flight attendant,
yeah.
there were like rejected landing and takeoff because the plane first hit the plane and none of the passengers knew.
Mm-hmm.
We would just keep it between us
Mm-hmm.
in case we had a crash landing.
Yeah.
Or one of the engines failed, and so we flew from like Texas to California with this one engine, and none of the passengers knew that we had to prepare for a crash landing in case we
Yeah.
fell out the sky.
Yeah. Yeah.
Half the time, the passengers don't know. Like
Mm-hmm.
that's
right.
But it happens a lot.
That's why you see sometimes the strained look in the flight attendant's eyes when they're smiling. They're like, right? Please sit down. Yeah. Yeah. Oh, I know. Yeah. Well, that's cool. Well, thanks, Paul. That's great. Yeah. And so let's look at how we detect some of these things. So these volatile compounds, like the chemical warfare agents and toxic industrial chemicals, they indicate a threat. They got to be detected by gas phase detection methods. So how do we detect explosives? Okay, so they're energetic materials. We talked about them in the last lecture, but they're not necessarily dangerous to handle. Okay, they're organic compounds. They have the oxidant inside with next to the fuel. But if we have a sensitivity scale, the really sensitive ones are dangerous to handle, but the more energetic ones are not necessarily difficult to handle. Sensitive primary explosives. It says too dangerous to handle. I mean, that might be the case for something like triacetone triperoxide. I mean, that frequently somebody tries to make that in their garage and they blow their hand off or something. So triacetone triperoxide. And you say, well, gee, I know acetone, right? That's fingernail polish remover. Yes, you can buy all the components for TATP. I'm going to write that out. TATP. In the hardware store. All you need is battery acid, acetone, and hydrogen peroxide. Okay. I'm not going to tell you the concentrations of the procedure or anything like that because I don't want you to blow your hand off. But it is so sensitive that it can detonate wet, and that's unusual. Most of these explosives, you have explosive powder or whatever, as long as it's kept wet, that keeps the heat, this activation energy, dissipated, and that's a safe way to store explosives, is to store them as a wet powder. Triacetone triperoxide will detonate wet. They say that there's almost no activation energy needed to detonate it. So if you insult it or look at it askance, it will blow up. Okay, so we've had people try to use it in a main charge, on a backpack or whatever, and just the jostling of getting to their target, they've blown themselves up. Okay, so that's what I mean by too dangerous to handle. Thank goodness this one is too dangerous to handle because, again, you can buy all the components at the hardware store. Now these over here, mercury fulminate, lead stiffenate, lead azide. These are in ammo primers. So you've got a gun cartridge, which we'll talk about in the next section of the course. You know, when you shoot a pistol or a rifle or any sort of firearm, the firing pin hits the primer, and that's a mechanical shock. And that needs to set off the reaction. That needs to cause the explosion, okay? And so you need something that has a very sensitive drop hammer here. And so this is the sensitivity scale. You know, this is the range of a firearm firing pin. It hits that metal primer and causes these compounds to decompose energetically. They create a spark that goes in and then lights the powder. Okay. Secondary explosives are less sensitive to detonation by dropping, static charge, friction, or firing pins, and so on. So this drop hammer test is used to rank sensitivity. So that's what's going on here. But notice this one, nitroglycerin. That's the one that, at least in this list, is really too dangerous to handle. That'll kill you fast. But they've blended it with other things to make it less sensitive. So this is the drop hammer apparatus. It's a paper from Lawrence Livermore. So you've got a weight here. That's the hammer. You lift it up a certain distance and drop it. And down in here, you've got the explosive. And the explosive is in an anvil with got a little sandpaper on below. So it's got a sharp surface and a little sandpaper on top and an anvil. And the hammer hits the top of the anvil. So the explosive is between two rough surfaces. And you drop the hammer and you have a microphone here. So this is a little microphone. It's a pretty simple device. So you have the mic, you don't have any explosives, you do background tests, right? You lift the hammer up and you drop it and it goes bang, and you listen to the signal. So you've got the normal signal for every, foot that you lift it up. And then you put the explosive in there and you drop it. Let's say you drop it from 2 feet, boom, and it's the same volume as nothing, then it was not an explosion. It was not an energetic reaction. You drop the hammer and the explosive goes off, then you have a louder sound. So it's a pretty simple device. You just listen to it and see if it makes a noise. Okay. This is a way to sort of turn what like if you hit explosive with a hammer and it goes pow, it went off. Well, you detect it with your ear. How do we get a computer to listen? So that's all this thing is get a computer to listen. And let's take instead of a hammer from the garage, let's build a repeatable hammer, a known weight on a nice thing that slides. For some of these big ones like TATB, now don't get TATB mixed up with TATP. Okay, this is triamino-trinitrobenzene. Okay, it's 50. Sometimes they put a greater than. Okay, so they don't have a 50-foot drop hammer apparatus. They just increase the weight. Okay. And so it is an enormous weight slamming onto this TATB before it'll go off. Okay. So that's the insensitive high explosive. So since explosives must be detonated, it would be nice if the user could just use a TATB, something that's really insensitive. TATB is so insensitive that they can shoot weapons that have it as their main charge. One of the tests was a 50 caliber machine gun round. So they can shoot it with a 50 caliber round and it not go off. It's going to damage the bomb and it's going to probably make it inoperable, but it's not going to kill the people who are driving it in the back of the Humvee. So it can be shot with a large round and still not go off. So that's the advantage of having insensitive munitions. It's also the advantage to the public to have insensitive munitions, because if you're driving down the interstate and the truck transporting these things flips over, which happens on 45, right? All these trucks run over things and run over cars and hit. You don't want those bombs going off, right? So they can be hit by other vehicles, they can be hit by trains and so on and not go off. So we like insensitive explosives. Okay. But insensitive explosives are also typically not volatile. Okay. An explosive train and also insensitive explosives are hard to get to detonate, right? You need an enormous force. Back here to the drop hammer, that's a large force. And you're not going to get that from a firing pin on a rifle. The little spring pushing a piece of metal against this is not going to give enough energy for TATB to go off. You actually need another explosive to hit TATB to make it go off. So we have to build an explosive train. We have to have a sensitive explosive that can be set off with a mechanical shock or a spark. And then that needs to go into a middle explosive that gives more energy and then go into the main charge. So this is the explosive train. We have an initiation event that could be an impact, like a contact detonation from an artillery shell where it hits, or it could be a stab like a firing pin where it creates a mechanical shock. It could be an electrical current, it could be heat. And that sets off that primary sensitive explosive. It starts to burn, starts to deflagrate, which is burning vigorously, and then it transitions to detonation. When a shock wave goes past supersonic, it starts traveling through the material as an energetic wave that breaks those covalent bonds and then allows the explosion to detonate. And then that goes into a main charge. So this main charge are typically non-volatile, which can range from kilograms to tons in size. So that's the big part of the explosive device that could cause a large effect, right? Either death or destruction. But the primary explosives are the ones that are volatile. So that's the stinky part of the bomb that we would detect if we're an analytical chemist. Okay. So explosives must be detected. We're going to be trying to focus on those primary charges and how to detect them. We have airport screeners, so you go in, you stand in front of the little terahertz screening thing, and it does the little sweep. And these are imaging techniques. So it's flagging people for further inspection, and it's kind of semi-remote. You can see this picture of this person. This is sort of a false image, but it's showing that she's showing up on the computer screen as green, but there's a shadow there. So she's got something under her shirt. Okay. And so then they would pull her aside and say, what's this under your shirt? And it doesn't have to be something nefarious, right? Maybe it's something she can't easily remove. If there's people out there that have, for whatever reason, have had to have their colon removed. So they have a colostomy bag, okay? And so it's a port, comes right out of their small intestine and goes right out the front of their belly. And it's a little plastic port with a little threaded deal, and you've got a plastic bag that you put over there, and your food just comes out into that bag after you've digested what you can get out of it. And then you take that bag off and dispose of it and put a fresh one on. So this person could have a fairly full colostomy bag under their shirt. Okay. And so it's not necessarily that this person is doing something bad, but it just may be part of their system. Now it's not going to catch on a metal detector because it's all plastic. And so, but it would show up on this imaging technique. Okay, we can use dogs, right? So volatile components can be smelled. We could train sniffer dogs, and we could also use instrumentation. We have GCMS and all different kinds. So let's talk about those different techniques. Okay, so here's the different vapor techniques. The first one I used in graduate school was this tunable diode laser absorption spectroscopy. And so the nice thing about lasers is they go in a single direction, right? They don't disperse very fast. If you just use a hot source, it disperses in all directions. And so if you're far enough away from the source, you have very little infrared light hitting the thing you're trying to analyze. Okay, you can try to focus it with lenses and mirrors and so on, but lasers are better. They have a low dispersion. So a laser goes in a straight line. You can bounce it back and forth between mirrors and get 20, 30, 40 passes. So in a small space like this, you might have like a 10-meter path length. So think about Beer's law, right? The absorption is equal to the EBC, the absorptivity of the substance, B is the path length, C is the concentration. Concentration's really low because it's gas phase detection. We're sniffing. So concentration's really low. So how do we get the absorption signal high? Path length. So we send this laser back and forth between two mirrors 20, 30 times, and our path length is like 20 meters. So then we go past this little patch of air and we are able to detect really low amounts of substance. This scientist that had this tunable laser system, he was detecting ammonia in people's breath because H. pylori bacteria, sort of an ulcer-causing bacteria in the stomach, would give off ammonia, and so he would have them burp, and he could detect the ammonia signal. It was super sensitive for ammonia. That was one of his applications that he wanted to develop. He said, though, it comes out of your pores too, and this machine, he said, could smell what he had for lunch. Like different days, he'd come in from lunch and his breath or whatever, he's just smelly, right? And his instrument is such a good sniffer that his baseline would move depending on whatever he ate. So I thought that was pretty sensitive. But it's really expensive and very fragile. It hasn't been commercialized. So you can't go buy one of these off the shelf and stick it in an airport or in a subway station. GCMS, man, that's the gold standard because it has separation and really sensitive detection. So think about the size of the samples, microliters. So it doesn't take much of a sample. It separates it and tells you the identity from the mass spec. So that's great, but it's too slow. You got to wait for that 30-meter column. Takes minutes. The screening for those luggage sniffers at the airport, that's about 6 seconds is what they're after. So they would like you to not spend more than 6 seconds per luggage. You swipe it, put it on the machine, move the next one, swipe the next one, just keep the queue going. Long path IR is very selective, but it's not as sensitive. Terahertz spectroscopy. So the thing you're standing in front of when it does the screening is a terahertz imager. It's not really a spectrometer. They're using it as a crude way to see through your clothes, but they're not using any spectroscopic information. Now, terahertz spectroscopy would get the rotation of molecules, and that would require a very large size difference between the molecules for you to determine whether it's like RDX versus HMX versus TNT. And it's pure rotational spectroscopy, so it has to have a permanent dipole moment. So if your molecule is symmetric, it's not going to detect it. So if you have a symmetric explosive, it wouldn't be able to be detected from a rotational spectrum. Okay, dogs are in this list too. Although you say it's not easily mass produced, you mean dogs reproduce, definitely, but the training is difficult, to train them on the different techniques. They've got a lot of different kinds of dogs. They have bomb sniffing dogs that sniff for the stinky parts of these primaries. They've got drug sniffing dogs, and they even have money dogs. So dogs that can smell large amounts of cash. And then we have the adsorptive techniques. So this is a kind of an interesting technique. You can take you can make a printed circuit board that then you expose to explosives. Okay, explosive vapor, and then you put polymer on that circuit board. And so this conductive polymer has the explosive in it, and it forms these pockets that are specific to a particular explosive vapor. And then you heat it up, and the small molecule leaves, and it leaves a pocket. And so now you've got like a perfect, not thumbprint, but imprint of that molecule in the polymer. And so if the explosive vapor comes along and finds that pocket, it's going to fit perfectly. So it fits in that pocket perfectly and stays until you heat it up and drive it out. So you've got a molecule-specific template in this little circuit. But you've got to make one of those little circuits for everything you want to detect. So that's why I say range of detection is expensive. So you can do this polymer surface treatment, this conductive polymer surface treatment, and with or without the explosive, it'll have a different signal. And so it's sniffing. It's like an electronic nose, and a lot of times they call it electronic noses. Because how does your nose work? You've got all kinds of little proteins on the surface of your olfactory bits, and the molecules land in there, and they give a different signal. And so this is an electronic nose. And then we have the ion mobility spectrometry. It has the benefits of mass spectrometry and chromatography in one vacuumless package. So you don't need a high voltage power supply. You don't need a vacuum pump. These are all good advantages. It's pretty inexpensive. It was developed for the U.S. Army to detect chemical weapons and used by the Coast Guard to detect narcotics. And it's what they use in almost all the airports. So this, when they swab your bag, this is what they're using. And then today, the reason I have to leave maybe a little bit early is the thesis defense by Jared Estevanes, who's doing a DART MS. So direct analysis in real time with a mass spec detector on the end. So this is another sniffer that has a mass spec on it. Okay, so I've got a few of his slides in here that we can talk about. But let's talk about IMS, or ion mobility spectrometry. This is the ion scan by Smith's Detection. You see this at the airport. They've got some fancy ones now, a little bit fancier than this, but this is what it looks like on the inside. So these are some of the images from their documentation. It's a pretty simple instrument. Notice, really, there are no moving parts, and that's also an advantage. You don't have any real wear and tear. So let's zoom in. So they, at the airport, you can take this little sample cloth here and swab your luggage, and the little swab goes into this desorber. So they put hot air through it. and the molecules come through here and they get analyzed by the detector. This also made, they implemented these things really fast. They already had them in the Coast Guard, and so as after 9/11, these showed up instantly. They're like, well, we can detect explosives with these same pieces of equipment. And that was, so I was supposed to start on, let's see, was 9/11, was it a Tuesday? I think it was a Tuesday. I was supposed to start the next Monday working at Pantech. So again, a national security facility, and I was supposed to start the week after that. So, and they make explosives there. So I worked in an explosives lab for 3-4 months, and then I needed to go fly for some training. Well, that was enough time for them to start implementing these in the airports. And so I go to Amarillo Airport to get on my plane. I've never flown. They had shut the airlines down for a while, and then when we brought them back up, they had these explosive detection equipment. And I've been working in the explosives lab for 3 months now, and wearing these boots. And I get there, and they say, "Can you take off your shoes?" And I was like, "Okay." So that's weird, but yeah, took off my shoes, and they got that swab, and they're rubbing it like right in the creases of the boot. And I was like, "Oh my gosh, I work in an explosives lab." Right? Are they going to detect my environment where I work? And they didn't, because apparently we have really good cleanliness in our lab. I thought we did, but I was very nervous. And anyway, so that was good. We don't have explosive powder just lying around. So that's a testament to the explosive cleanliness that we have. So here's how it works. Most of the time in mass specs, you have a high voltage source to produce an electron beam, like electron ionization, and that beam of electrons will ionize the sample. So EI, ionization. But that comes with the cost of the bulky power supply and the power requirements for running the power supply. And so another way to produce high energy electrons is a radioactive substance. So here's a nickel 63 source, and it's spitting out beta particles, which are high energy electrons. So those beta particles come out and they ionize the substances that are in this inlet area. What actually happens is they ionize a little tiny dichloromethane gas. So there's always a little sample of gas to go in there and become ionized. And so you have an ionized gas in there, and then that ionized gas will hit your molecules and transfer the charge to your molecules. So it'll either transfer a negative charge, which typically happens to explosives, or it'll steal an electron from narcotics. So narcotics are typically positive in these environments. But now I've got negative explosives, negatively charged explosives, so PETN, HMX, RDX. And over at the other end of this tube is a positive detector. They call it a collector. So my negative molecules immediately see the positive end of the road down there and start heading that way. And they have to pass through this counterflow of air. So there's a little filter there, so it's mostly nitrogen and oxygen. It's flowing in this direction. So this is the crowded sidewalk or the dance floor, more like a crowded sidewalk when you're trying to go one way and everybody on the sidewalk's going the opposite direction. So this is ion mobility. It's not really like time, this looks like time of flight mass spec, that these molecules will be accelerated by the same force, but the mass would cause them, the difference in mass would cause them to have a different speed, okay? So you've got a minus charge and a positive charge. You've got a set force, and force is equal to mass times acceleration. So if you have a higher mass, you have a slower acceleration. You have a lower mass, you have a higher acceleration. So the smallest molecules would accelerate faster, and the heavier ones would accelerate slower because they have the same force on them. Well, that takes a while for you to really separate like a distance. It takes a long tube for you to have high resolution in time of flight mass spectrometry. So the way this gets away from having a long tube, they can have a shorter tube if they have a counterflow of air. But that's not true time of flight. The ions have to make their way through this counterflow of gas. And so that's what the mobility part is in the name. So the ions have to be mobile through the gas, and that's going to provide a little different method of separation. So it's not true time of flight, it's ion mobility. So that's why it's IMS. Okay. So the grid pulses the ions down through the drift tube against the counterflow of dry air, and narcotics typically go towards a negative electrode and explosives towards a positive electrode because of the different charges. So ion separation is based upon the unique combination of molecular size, because they got to go through the counterflow of gas, and the mass to charge ratio. So this is what the signal looks like. The ions impact the electron capture detector, and a plot of signal versus time forms what they call a plasmagram, because it's an ionized gas. So this is the time in milliseconds. So notice a full scan only takes 20 to 25 milliseconds. So it's really fast. So you can do this over and over again and get lots of scans in a given second. So this is what they call a waterfall plot. It's a lot of plasmagrams put on top of each other. So each one of those is called a segment. So each one is a segment. You see number of segments here. Each time is called a channel. So like this would be a channel here. Sort of it's kind of tilted away. So this would be a different channel. So those peaks show up at different channels. And then you've got some quality control issues. You've got a certain width to the signal. You've got a maximum amplitude. You've got the number of segments it shows up in and the total amplitude. So this would be like an integral. Right? You wouldn't want to just have a blip, like one single plasmagram. That would be less reliable than multiple plasmagrams. So the integral signal would be important too. So you have these quality control criteria. So your software asks, does it match the drift time? So is it the correct channel? So let's look at, say, HMX. So if it's 1.3 plus or minus 45, I don't know what the 45 is. It's certainly not the first digit here. It might be some sort of percent number. So I don't exactly know what the units are on the variability, but it matches the drift time. It has a certain full width at half maximum. It can't be much greater than that, because it could just be like the system could just be flooded with lots of molecules, and it may not be specifically HMX. And so it needs to be a defined peak at the HMX drift time. Okay, so the full width half maximum needs to be less than the 365. The amplitude has to be above a threshold of 25. And then it needs to be in 2 or more consecutive segments. Okay, so we've used all of these. I don't know what this one here is, so that's the only criteria I don't know. But this was the table of settings that you can pull out of the software. And in the Smiths detection software, you can go in and you can set new settings if you have a new thing that you want to detect. So that's nice. It's pretty versatile. So if you get all of these criteria, then ring the bell, right? And the machine goes crazy when you actually detect something. It's like ding, 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 and then the screen flashes red and everything like that. So the TSA person can't ignore it, right? It's gonna make a signal, yeah. Okay, so now let's talk about DART. This isn't in your notes. This is stuff I added just this morning, because this is Jared's PhD thesis that he's defending today. So we can all wish him luck. And it's for the detection of explosives and explosive residues post-blast. Now, he's not really evaluating it for pre-event sniffing, but this direct analysis in real time could theoretically act as a sniffer, okay? He's wiping and putting the wipe in front of the sniffer, and it's sniffing the compounds off that wipe, okay? These are some of the things that they're doing. They're building these with the Montgomery County Sheriff's Department. They're building these homemade bombs and putting explosive charges in here, or pyrotechnic, and then they're analyzing how much explosive residue is on the 9-volt battery, or on the circuit, or on these screws, or different plastic components and tape and so on. So they're trying to see if, let's say, a metal, like one of the ones, they didn't detect this particular explosive on the metal because the metal seems to catalyze its destruction, perhaps. Okay, it's not stable on a metal surface, or maybe the metal surface is not sticky enough for the explosive residue to stick to it. Whereas the plastic, there's lots of this particular explosive on the plastic. So they're sort of providing some insight into the flow chart of analysis of bomb post-blast residue. So you would look at, let's say he's successful, you'd be using his work, if you're responding to a post-blast situation, and you would say, well, I'm going to detect, say, ammonium nitrate on the plastic parts, and so I'm going to swab those and look for ammonium nitrate on the plastic parts, and I wouldn't look at, say, the metal parts for that particular substance. He's also looking at Raman spectroscopy and polarized light spectroscopy and looking at pyrotechnics. So here's a bunch of pyrotechnics, and this is some of the compounds that they can detect, just even looking at the crystal structures. So this is the barium nitrate, potassium chlorate, and the potassium nitrate crystals. The nice thing about this is this microscope is connected to a Raman microscope, and so you can focus the laser even onto a small part of the crystal, so they can shoot the laser right there and they can get this Raman spectrum. So that's super cool. Okay. And then they can identify and make a database for these different peaks. And then this is the mass spec, that's the high resolution mass spec that is attached to the DART sniffer. And so you have the sort of the ionized gas inlet. It's producing the ionized gas. You can put your swab here in the way, and that ionizes the molecules on the tip of your swab, and then it collects them, focuses them down, and you have this orthogonal accelerator. So the ions are going to the right, and then you hit a pulse and it drives them all down this way. So they go down here, and then they go through this thing called an ion mirror. Okay. And so the ion, let's say the ions are negative, they come down and they hit this negative charge zone and they turn around and go the other way. And it's a way to just make this a longer flight time, which gives you higher resolution. So they can have super high resolution mass spec. So here's some M over Z. You can see here's trinitrotoluene minus a hydrogen. So that's the peak there. If it, say, loses an NO group, then that's this peak here. So you can see these different fragment patterns, and you can positively identify the substance. And this happens really fast, and you get high resolution spectra because we're not going through the 30-meter GC column. So this is a way to sniff and go straight to mass spec. Now we can talk about the other threat, biological threats. And so this is, we've experienced this, didn't we? Okay. And do you ever play this game, this Outbreak game? Man, what a crazy game that was. The downloads went nuts during COVID because everyone was like, check this game out. Let's terrify ourselves, you know. And so this is an article by the New York Times talking about Plague Inc. And it was really hard. I mean, you learn from the game. It's really hard to create a pandemic that would go worldwide and so on. Before COVID, my example in this part of the lecture was using the West Nile virus. Okay, the West Nile virus was a really interesting pandemic. There was a case in New York City, and it was deadly to some people, but it wasn't. It had a really low mortality. It could cause brain swelling, encephalitis, and that could be fatal in severe cases. But it was spread by mosquitoes. Now, how's a mosquito going to get all the way to Texas, right? Especially when they die out in the winter. So if you have a harsh winter, the pandemic's over, okay? They had a reservoir species. So the mosquitoes would infect horses, and the horses would carry it through to the next season. And then the mosquitoes would bite an infected horse, pick up the virus again, and start transmitting it again. And so you had a vector, which was the mosquito, you had a reservoir, which was the horse, and then you had the people that were getting the virus and suffering side effects. Okay. So it only took, I'm trying to remember the dates, it was like 3 years, 2 or 3 years before I got it in Texas. It's like it spread from New York, then it was the Northeast, and then it went all the way across the Midwest and the Plain States, all those horses. Okay, and then it went all over the whole country. Now, if the virus has too high a mortality rate, then it doesn't spread. If it has a too low mortality rate, it's not a serious threat. So it's a weird balance between those things. Now, the thing is, it's really hard to stop because it's not necessarily something volatile. Like, we don't have a breathalyzer to tell. You have to have these ELISA tests or other kinds of tests. to interact with the substance. And so there really was no analytical way to stop it. And how are you going to stop a virus that we're not immune to? I mean, you can compare Sweden and Michigan. They're about the same, latitude and so on, and look at their two responses. And I'll just leave you with that. And you can make your own conclusions. So we do our best to prevent by using these biosafety level setups. And so this is biolevel safety 4, where you're dealing with things like Ebola and some of these modified coronaviruses and so on. These were dangerous and exotic agents that pose a high risk of aerosol transmitted laboratory infections and life-threatening diseases. And so what do we do for biosafety level 4? Everything passes through an autoclave, okay, when it comes out. So it's completely sterilized on the way out. And all of your garb, you're in a positive pressure suit. So you suit up in these positive pressure suits. You have supplied air, so you're not breathing anything in from the laboratory environment. So this is how you have to work in a biolevel safety 4 facility. Okay. So I don't know what to do in terms of biological threats. So I'm really at a loss. Explosives, industrial chemicals, warfare agents, they're all pretty volatile, and we can sniff them. We're just trying to find faster ways to sniff them, cheaper ways, and more reliable ways to sniff. So we're trying to make mechanical dogs, right, that we can install and put in different places. So a pilot describes flying as hours of boredom interrupted by seconds of terror, right? And we hope the days of terror are small, right? We hope to have years of boredom. And as a forensic chemistry major, the world will depend upon you to do the 3Ds. It's not going to always be after the fact. Some of these situations are severe enough that you need to be in front of the threat, and you need to be able to detect it earlier. Okay. So here's some of the references that I have, and then Jared's thesis. So after today, I'm sure his thesis will be available. It's pretty good read. 260 pages though. So so props to him for doing such extensive work.